All right, Calc BC, good morning. It's Wednesday, May 6th. We've got a new mock exam question. It is the question number one, the longer of the two, 25 minutes. And I want to run through it with you my first time. I haven't seen the question yet. I just printed it out. And I've got my timer here about ready to go, 25 minutes. And what I want to do is get my pages set up ahead of time. You do this after you log in and before the test starts. You've got your AP ID number, your initials, and then the page number. I forgot to talk about adding the initials. So you got your AP ID, the initials, and the page number, and have all five ready to go. Okay, so you got your AP ID, initial, page number. You got 5 pages. And you've actually got 2 sets of 5 right before the test starts because it's 2 problems, 5 pages each. You don't want to have to worry about stressing about getting that ready to go. Okay, so we've got the 5 questions, and I just made it just in time on that first question that came out, which was actually question 2, which we had 15 minutes for. So this one gives us 25 minutes, and what I'm going to do is the moment I see the question, I'm going to parcel this thing out somehow. If it's got 5 parts, I'm happy. I'll give 1 page per part. If it's more than 5 parts, I think I'm going to go with a half page for each one and then use any additional blank pages for extra space if I need it. And I let the reader know, hey, I needed more space, so look at page 5 or whatever page I'm going to go to finish the problem. All right, so here we go. 25 minutes. You've got at least a couple of pens or pencils ready to go. Let's see how we do. All right. You have 25 minutes to complete this problem plus 5 minutes to upload. All right. So I've got A, B, C, D, E, F, G. A, B, C, D, E, F, G. That's 7. That's more than 5. All right. So A, B, C, D, E, F, G. All right, so I'm giving myself a half page per problem. Let's get started. I had a feeling we were going to be given a graph. The continuous function f is defined on the closed interval. So this is the graph of f, the original function, not the derivative, -2 to 5. Consists of 2 line segments, so these are straight lines, and a quarter circle. That's important that we know the equation of this, right? It's got the center point at 5, 3, meaning it has a radius of 3. All right, the function is given by, so there's this new function g, which is this variable limit function, which is the accumulated area under the curve function. A, find the average rate. Okay, average rate. Average rate, not average value. Okay, right? So average rate is like an average slope. So let's just change in y over change in x over the interval. All right, so the change in x is 5 minus -2, hashtag DNS. And then I need to find, and it's the average rate of change of g. Okay, so I need to do g of 5 minus g of -2. Okay, so I just have to find what g of 5 and g of -2 is. So g of 5 is the integral from -2 to 5 of f of t dt, meaning that is the area under the curve. Okay, so going back to this thing, the area here and the area here cancel out. All right, and so from here to here, they're canceling out again, right? So that's a net 0 from -2 to 1. And so now I have to break this up maybe into this box. That's an area 1. And this is a base times height divided by 2. So this is 1.5. And then this whole thing is a 3 by 3, 9 minus a quarter circle. So this area in here is 9 units because of the whole square minus the quarter circle, which is pi r squared over 4. Right. Okay. So it's the whole box 3 by 3. Take away the quarter circle will give us the area under the curve. The whole circle is pi r squared. A quarter is a fourth. All right. So g of 5 is equal to 2.5 plus 9 minus pi 3 squared over 4 minus g of -2. Well, g of -2, well, is 0 because it's the integral from 0 to 0. So it's minus 0 over 5 minus -2, and I'm done. That's the average rate of change, average slope, change in y over change in x. Part B. Find the limit as x approaches -1. I'm assuming this is going to be L'Hopital when it gives me that. Let's take a look. So the limit as x approaches -1 of f of x squared minus x over f prime of x minus x. Okay. Well, try to plug it in. So that would be f of 1 minus 1 over, minus a -1, I think. Yeah. So -1 squared is 1, so it's f of 1 minus x, which is -1, all divided by f prime of -1 minus -1. Okay, what's f of 1? F of 1 is 1, so that's going to give us 1 minus a -1. So it's not 0 over 0. F prime of -1. F prime of -1 is the slope of the tangent line at -1, and that is -1 minus a -1. So that's 2 over 0. So the limit doesn't exist. Oh, I wrote it down wrong. It's a plus here. So it's a plus here. So it's a plus here. It is 0 over 0. Good. I had a feeling it wasn't going to be that easy. Okay, so you cross out the 0 over 0 and you say, using L'Hopital's rule, this limit now equals this new limit. It's the limit as x approaches -1 of the derivative of the top, which is going to be f prime of x squared times the derivative of x squared, which is 2x, chain rule, plus 1, because the derivative of x is 1, over now the second derivative of f at x, minus 1. Okay, so let's try it out. We've got f prime of -1 squared, which is 1, times 2 times -1 plus 1 over f double prime of -1 minus 1. Okay, f prime at 1 is 2. F double prime at -1, that's the second derivative. And so since the derivative is a constant because it's a line, the second derivative is 0. Okay, this is not 0 over 0. It's some value. I don't know what it is, but it's a value. I'm moving on. I'm done. I'm already 2 parts done. Part C. What does part C say? Part C says, for the interval -2 to 5, find all values of x for which the graph of g has a point of inflection. Point of inflection. That's when the second derivative is 0 or undefined and changes sign. So I'm going to have to find the critical points for i.e. when the second derivative is 0 or undefined. All right, so I need to remind myself what g is. G of x is equal to the integral from -2 to x of f of t dt. Okay, so g prime of x is going to equal the derivative with respect to x of the integral from -2 to x of f of t dt. Some of you might know the shortcut. I don't want to assume you know it, so let's go through it. It's the fundamental theorem. It's the derivative with respect to x of the antiderivative, which is capital, evaluated from -2 to x, which is the derivative with respect to x of capital F of x minus capital F of -2. Capital F of -2 is a constant that goes away. So the derivative of capital F is lowercase f. The derivative is f itself, which we see the graph of. And g double prime is equal to f prime. All right, so I want to set that equal to 0. When does that equal 0? That happens when x equals. When is the slope of the tangent line 0 or undefined? 0 or undefined when x equals 0 and 2. Okay, and we need to talk about how we know it's a point of inflection, and that's if the second derivative is going from positive to negative or vice versa. And so since we're looking at f prime is g double prime. And so when does f prime change sign? When does f go from increasing to decreasing, right? Like if I want to know when this is going from positive to negative, I want to know when this is, when the original function is going from increasing to decreasing or vice versa. So these are both inflection points. Because they are points in which f prime of x changes from positive to negative. That's when x equals 2. Or from negative to positive. That's when x equals 0. I think that's enough. I'm going to come back to it and try to tidy it up if I can later, maybe. Part D. Evaluate the integral from 2 to 4 of f prime of 6 minus 2x dx. This is a really nice looking problem. You're asked to find an integral of a derivative. We don't know the function, but we do know that this thing looks a lot like maybe you're taking the integral of a composition of functions where the thing inside the box is a line. Whenever that happens, u substitution works nicely. Let u equal 6 minus 2x. du equals -2 dx. dx equals du over -2. Let's do some direct substitution. And actually, I'm gonna change the bounds too. So when from this I can change the bounds. If I know the x's, I know u's. So when x equals 2, u equals 2 minus 2 times 2, or 6 minus 2 times 2, which is 6 minus 4, which is 2. So now this is going to be the integral from 2 to, when x equals 4, u equals 6 minus 2 times 4. And that's going to be 6 minus 8, which is -2. Interesting. Okay, so -2 to -2 is how that is going now. And it's f prime of u, and dx equals du over -2. There's a constant multiple there. Let's factor that out. So this is -1/2 times the integral from 2 to -2 of f prime of u du. All right. Well, fundamental theorem, that's going to equal -1/2 regular function because the antiderivative there, f of u, and that's going to be evaluated from 2 to -2, and you're going to subtract. So it's -1/2 times f of -2 minus f of 2, and that's -1/2. F of -2 is 1 minus f of 2, which is 3. That's a value that my calculator can do, so I don't have to. I'm moving on. So far, pretty smooth. Okay, we got 12 minutes to do a couple more problems. And it now gives us a new set of problems, actually. So let's take a look at that real quick. All right, so we've got a new function h. You can take derivatives of it. Graph of h is shown above with the line tangent to the graph of h. Okay, so h is this curvy function. And this is the tangent line at x equals 0. Okay. Selected derivatives. Okay, so this is like the nth derivative, right? So we've got the second derivative here, we've got the third and the fourth. Well, I think we should continue it and write down 1 and 0 because this, to me, has the feel of a polynomial, a Taylor polynomial, where you're going to need to know the nth derivatives. So the first derivative is the slope of the tangent line, and that's what they gave us. And let's look at the lattice points. Here's a lattice point, here's a lattice point. You're going down and over, so the slope of this tangent line is down 1, 2, 3, 4 over 2. Negative 4 over 2 simplifies to negative 2. The first derivative at 0 is negative 2. And the 0th derivative is the point, and so that point is 3, the location. So now we need the third degree Taylor polynomial. So I know the third degree Taylor, so let t sub 3 of x be the third degree Taylor poly. Oh, I should be writing this on my other one. Okay, let's go back to this. And I was using p, so I'm going to say let p sub 3 of x be the third degree Taylor polynomial for h about x equals 0. Okay, so p sub 3 of x, we're centering it at 0, is going to be f of 0, no, it's h of 0, plus h prime of 0 x plus h double prime of 0 over 2x squared plus h triple prime of 0 over 3 factorial x cubed. All right, and I know all those things. So h of 0 is 3, h prime of 0 is negative 2, h double prime is 3, and h triple prime is negative 323 over 2 over 3 factorial x cubed. Done. Okay, F. Write but do not evaluate an integral expression that gives the volume of the solid when rotated about y equal negative 2. Does it tell us what a region is? Oh, yeah, it does. So R is the region bounded by the graphs of H. Oh, it's this highlighted region here. Okay, so the line y equal negative 2, that's way down here. So just draw a random horizontal line and say, okay, that's my volume of solid revolution. And so this is going to be a washer. There's a little r, and there's a big R, and there's a little with dx, so I know it's going to be a dx thing, and these are big y's minus little y's. Okay, it looks like I'm going to need the slope. I needed the equation of this tangent line here. So the equation of this tangent line, since I know the slope is negative 2 and I know a point, I could probably go just into y equals mx plus b form since I know that stuff. So y equals mx plus b, y equals slope negative 2, x plus 3. Okay, so I needed that. All right. And if I didn't have this printed out, that would be kind of a disadvantage. So we almost would have to graph it on our paper too. So I kind of want to model that and show that you do have enough time. We're at 8 minutes. And you know, I really haven't been looking at it too much because if you spend your whole day looking at a scoreboard, you're gonna lose the game you're playing. So terrible, just really bad, but it's enough. It was a bad drawing, but I don't care because I want to just get the gist of it down and make sure I've got my big R and little r figured out. Okay, so I know volume is the integral of area, and it's going to be a dx, so I can have those x values figured out right away. That's the integral from 0 to 1. And I know area is equal to pi big R squared minus pi little r squared. And I know big R is going to be a big Y minus little y, and that big Y is h. And I don't think they're giving me enough information on h, so I think I'm just going to have to write it with h in there. So big Y is h, little y is -2, and little r is also a big Y minus little y, and that's the one that I found, which was, this was y equal -2x plus 3. That's also minus a -2, hashtag DNS. I've got my integral set up. I know what area needs to be. I figured out what those little parts are. Don't forget to square them. So now volume equals the integral from 0 to 1 of pi big R squared minus pi little r squared. Don't forget the differential at the end. I think we're good. I think that's the best we can do. We'll see. All right, one more to go. G. Evaluate the integral from 1 to infinity. Whoa. Okay, well, that means it's going to have to be something either like a geometric series look or an integral thing that we can actually evaluate and take the limit of. And I think you're going to get a point just for rewriting it as a limit. So this is the integral from 1 to infinity of 1 over x to the p plus 1 dx. I feel like I've done this with you. And p is greater than 0. I think we've done notes on this. So this is now equal to the limit as t goes to infinity of the integral from 1 to t of x to the negative p minus 1. If you just bring the integral up, I think. Yeah, you're just going to negate it. Okay. So then now that equals the limit as t goes to infinity of x to the negative p minus 1. When you take the integral, you increase the degree, so you add 1, and then you divide by that same amount, negative p minus 1 plus 1. All right, from 1 to t. Remember, p is a constant, so you're plugging in for x. Okay, so now I don't... Excuse me. Excuse me. Okay, so this equals the limit as t goes to infinity of perhaps, like, I don't even need to evaluate t yet. I'm just going to clean this up a little bit. So this is x to the, so the minus 1 plus 1 goes away, right? So it's just x to the negative p. That's kind of nice. And then I think the same thing's going to happen here, negative p. Okay. And I think I could clean it up even more because of the negative exponent. I can bring that down. So now this is going to equal the limit as t goes to infinity of 1 negative 1 over px to the p. And remember, p is greater than 0. So it doesn't matter if p is 0.1 or 1 or 2. Because p is positive, this thing in the denominator is getting bigger. If you're thinking about the final answer here. All right. So when I subtract, I'm subtracting the negative, so I made that positive right away. Hopefully that was okay with you. And as t goes to infinity, this denominator grows and this numerator stays constant. So this limit is 0. So the limit of this thing equals 1 over p. And I believe we are done. With 2 minutes left to spare. That's not a whole lot of time left to spare. And I know I maybe made this look easier than it was. But 2 minutes is a decent amount of time. And you will do better if you practice this. So now I just want to take a moment to look through this and double check I didn't make any silly errors. I really recommend when that timer goes off and you have 5 minutes, you just stop and you just take pictures and you turn it in. Okay. So couple things. Average rate is average slope, not average value. It's not integral over interval. It's just slope between the endpoints. And so we were taking accumulated area under the curve. Accumulated area under the curve. And from -2 to 2 is 0. So that g of -2 equaled the integral from -2 to -2 of f of t dt. So it's the area under the curve from -2 to -2, which doesn't make sense because there's no width. So that's going to equal 0. All right. And then part B was a L'Hopital's rule. Whenever you see a limit like that, you're expected to get 0 over 0. I didn't at first, but I made a mistake in copying the problem down wrong, right? The tricky part, I think, in L'Hopital's rule is crossing out the 0 0 and then stating that using L'Hopital's rule. If you don't state that you're using L'Hopital's rule, I don't think you get the follow-through points. It's very tricky. Tomorrow we'll have Steve Kokoska, I believe, talk about this problem again. Part C, fundamental theorem of calculus, and then I think I did well on that inflection point. We'll have to see. Part D, use substitution. I changed the bounds, but I think you could figure it out without changing the bounds. Come to office hours if you want to talk about that. Part E, that third degree Taylor polynomial, you've got to know this cleaner setup of it. Yes, it's nice to know the sigma notation of a Taylor polynomial, but cleaning up the first 3 terms before getting to factorial, and my time's up. So I'm just going to stop it there and post this for you guys to look at. And I want to see your initial work as well. So before you watch me do this, I hope that you have done it first and then you're doing it again with me, something like that. Perfect practice makes perfect. All right, folks, thank you very much. Only a few more days. Let's stay strong. So long.